Now, we're going to talk about transformations. I just want to remind you of what we covered the last class. By the way, please remember to post a comment with your name or alias and your day and time that your class meets. So I see several of you have done that already. So on our last class session, we talked about the library of functions, the identity function, square root function, absolute value function, cube root function, and reciprocal function. And we went through the key points that I'd like you to graph for each one of those functions. For example, on the square function, let me zoom in a little bit here. The key points were 0, 0, 1, 1, and negative 1, 1. On the cube function, I always want you to graph 0, 0, 1, 1, and negative 1, negative 1. On the reciprocal function, I want you to graph the key points 1, 1, and negative 1, negative 1, and then the two asymptotes, x equals 0, y equals 0. On the square root function, 0, 0 is the terminal point for this function. It doesn't continue through that point, it ends there. And then we have 1, 1 and 4, 2. Remember, whenever you have a root, it's going to be a sideways looking function. Like this looks like half of a parabola sideways. The cube root, again, looks like the cube function except kind of turned on its side and flipped. This goes through 0, 0, 1, 1, and negative 1, negative 1. And then the absolute value function goes through the same three key points as the square function, but it's a sharp point at 0, 0 instead of a curve. So we have this V shape. Hold on one sec. Okay, and so why these key points? Because those are the points that we move around when we do our transformations. So sometimes when we do our transformations, I won't give you an equation at all. All I will give you is a graph like this one. And what we're going to do is to perform transformations on it without knowing the equation. And so the way that we do that is we represent this as y equals f of x. And I'll ask you to graph something like g of x equals okay, sorry about that. So we have g of x equals, and we'll take our function, whatever it is, whatever the equation is, and we'll say add 3 to it. Okay? So just to remind you, when you add a number to a function and it's on the outer part of the function, remember we talked about the outer and the inner. So this is on the outer part of the function because it's not inside the parentheses. When you do that, it's always going to affect the y coordinate. In this case, it's going to affect each y coordinate by adding 3 to it, which has the effect of moving it up 3 units in this case. But all you need to do is look at certain key points on the graph where important things happen and move them around. So if we're talking about a graph that's not one that we've memorized, but just one that's given to us like this, just list the key points. Like, for example, instead of going through negative 2, 0, our new graph is going to go through negative 2, 0 plus 3, which is 3. Another important point on this graph is 0, 3, right? Because it turns around at that point. So we want to see where that goes, where we have that sharp point there. So we're going to add 3 to the y coordinates. We'll have to go to 0, 6. Another important point on the function f appears to be 2, 0. So on the new function g, we're going to add 3 to the y coordinate and we'll have 2, 3. And another important point down here looks like the point 4, negative 3. So we're going to take that point 4, negative 3 and we're going to add 3 to the y coordinate, and that's going to put us at 4, 0. And the last point on this graph that we're going to consider is the point 6, 0. That's going to move to 6, 3 when we add 3 to the y coordinate. Now every time we add 3 to the y coordinate on the graph, that's going to have the effect of moving it up, right? 3 units. So for example, we had negative 2, 3. That's going to be here. And we have 0, 6. That's going to be here. See how it's 3 units above where it was before? And 2, 3 is going to be here. By the way, I like you to label them on the graph, so when you take your test, remember to do that. We have 4, 0 here, and 6, 3. Okay, and then we're going to just connect the dots. The shape stays the same. When we have a vertical shift, this is called a rigid transformation. Probably can't tell, but that's supposed to be a straight line segment. There we go. Okay, and so it's the same shape but shifted up 3 units. So you can either actually, perform that operation on the graph, or adding 3 to every y coordinate and then put it on the graph. Either way is fine. All right, so when we add to the outer part of the function, it's going to have a vertical shift. Also, if we subtract, it would just shift downwards, right? Another type of transformation we talked about would be if I wanted to graph, say, g of x equals f of, and I said x minus 1. Okay, so I'm going to erase the graph that I have here. Remember, this is being recorded, so if you want to look back at it, you can. But I'm going to erase that graph and say, what happens when I perform the operation of subtraction on the inside, the inner part of the function? Let me say inner. And if you recall from class, the effect that would have would be on the x coordinate. And it's always the opposite of what you would think when it's the inner part. So when we subtract 1 from x, we sort of have to increase each x by 1 to compensate, so we still end up at the same y coordinate. So we're going to do the opposite operation. We would add 1 to each x, which has the effect of shifting it to the right one. So we would, instead of being at negative 2, 0, for example, our graph would be at negative 1, 0. Instead of being at 0, 3, it would be at 1, 3. Instead of being at 2, 0, it'd be at 3, 0, and so on. Everything's going to shift just 1 unit to the right when we increase each x coordinate by 1 but keep the y coordinate the same. So our graph would be shifted horizontally. This is a horizontal shift. Okay, and again, if you were doing this on the test, I would want you to label where your new coordinates ended up. So I'd actually want to see the coordinates next to each point. All right, so vertical shift, horizontal shift. I'm going to erase these points here. Okay, let's look at, I'm going to move this guy up. Oops, missed him. There we go. Okay, now we're going to look at another type of transformation that we already talked about. I'm reviewing these because we're going to put them all together in different combinations, so I want to make sure everybody remembers how to get each one. So adding to the outside of the function, we're going to get a vertical shift, add or subtract really. subtract or add to the inside of the function, you're going to get a horizontal shift. Another type of transformation we did was where we actually negated the outside of the function. Again, if the negation is on the outer part of the function, it's going to affect the y coordinate. How is it going to affect it? It's going to negate it in this case. It's going to take the opposite. Okay, so what's going to happen when we take every positive y and change it to a negative y is that it's going to flip over the x-axis. So this is what's called a vertical reflection. Okay, so for example, anything that's got a 0 y value is going to stay the same. So on our graph here, all these points on the x-axis, they're going to stay right where they are. But for example, the point 0,3, we're changing the y value to -3, so it flipped down this way. And the point 4, -3, we're changing the y value to a positive, so it flip up this way. So you end up getting a reflection of the original graph over the x-axis. Okay, so it looks something like this. A vertical reflection when you have a negative outside or out front of the function. All right, what if you had a negative inside the function? You might have guessed that if you had f of -x, you're replacing each x with a negative x, so you're going to reflect over the y-axis or get a horizontal reflection. In other words, take a look at that. So we have a horizontal reflection. And what that looks like is, see this point 6,0 here, that's going to go way over here to -6,0. The point 2,0 is going to go to -2,0. And the point -2,0 is going to go to 2,0. The point 0,3, well, if you change 0 to -0, it doesn't change, right? So that's going to stay the same. And then this point 4, -3 is going to change to -4, -3 over here. So we're going to get a reflection over the y-axis, and our new graph is going to look like the mirror image of the original graph. Messy, sorry. Okay, so negative inside the parentheses, you get a horizontal reflection. And then the last thing that we did was a stretch or compress, which happens when we multiply the function by a value. So let's say I wanted to stretch g of x. By the way, let me check to see if you guys have posted any questions in the chat. Let's see here. So far, so good. You can always post questions in the chat if you want to, or you can even Skype a question to me if you have one. Okay, so another thing we can do, as I was saying, is you can stretch the function out by multiplying it by a value greater than 1. So for example, we could have g of x equal 2 times the original function f of x. Again, since the 2 is on the outside of the function, the outer part affects the y-coordinate, you'd be doubling every y value. So 2 times every y. So this gives us a stretch away from the x-axis. So for example, well, when you multiply every y value by 2, the ones that already have 0 for y, they're not going anywhere because 0 times 2 is still 0. But, for example, the point 0,3 becomes 0,6, and the point 4, -3 becomes 4, -6. So we get the effect of stretching the graph away from the x-axis. So it looks kind of like this. Oop, gotta move that guy. It's hard to draw straight lines on here. Okay. Oops. Okay, so we get the same shape, this kind of squiggle, the zigzag, but it's stretched away from the x-axis. And then something we didn't get a chance to talk about in class is, oh, and what we also mentioned that if that had been instead of a 2, like a half, you would compress it closer to the x-axis. What we didn't get to talk about was what happens if we multiply inside the function. So what if we wanted to graph g of x equals f of 2x? Okay, so just like before, when we had the subtraction here inside the parentheses, it ended up adding to the x-coordinate. If you multiply inside the parentheses, the inner part of the function, it's going to affect the x-coordinate in the sense that we're going to have to double or take half of each x-coordinate rather, in order that when we plug the x value in, we still get out the same y value as before. So it does the opposite of what you would think. So you're going to take half of each x, or divide x by 2, however you want to think about it. All right, so if we take f of 2x, we're going to get something that's half as tall as the original. It's going to be compressed. Oops, sorry, thinking vertical. This is a horizontal, my mistake. So it affects the x-coordinates, so we're taking half the value of the x. So anything that's an x with a 0, like 0, 3, has a 0 x-coordinate, doesn't move, because when you take half of x, it's still at 0. That'll be the same. But for example, -2, 0, that's going to change to -1, 0. And 2, 0, take half of 2 and you get 1. Oops. And 4, -3 is going to move to 2, -3. And 6, 0 is going to be way over here at 3, 0. So what happens is we get squished closer to the y-axis. A horizontal compression is what that's called. Whoa, going crazy on me here. Hate it when that happens. Sorry guys, I'm having trouble drawing here. Hold on. I think there's a delay. Let me try something. Well, that's working. There we go. It's back. All right. So it's squished closer to the y-axis by a factor of 2. It's half as wide as it was before. And all right, so these are all the different possible transformations that we discussed in class last time. And now what I want to talk about is what happens when we put more than one transformation together. All right. So when we have a variety of different transformations going on inside of one function, the order in which you perform the transformations is really, really important. And the order which our book uses, there's a couple different ways you can think about the order. So if you've taken a class before and learned a certain way of remembering the order of transformations and you stick with that and it works, great. But the one that's in our textbook, we have, you do any horizontal shift first. Remember, a horizontal shift is when you add or subtract a number to the x inside the parentheses. Then you do any stretching or shrinking. Remember, stretching or shrinking is when you either multiply a number times the outside of the function, or you multiply the number on the inside of the function. If it's on the outside, you get a vertical stretch, or a vertical compression if the number is a small fraction. Or if it's on the inside, you get a horizontal stretch or compression. If the number is bigger, you get a compression. If the number is smaller, between 0 and 1, you're going to get a stretch, actually, away from the y-axis horizontally. And then next, you're going to do any reflecting. Reflecting occurs when you have a negative out front or a negative inside the parentheses. So this would be a, remember when we negate the y, the f of x is just y, so when we negate the y, that's going to give you a reflection over the x-axis. So that's called a vertical reflection. And if you negate inside the parentheses the x, this is going to give you a horizontal reflection. And then lastly, you do your vertical shift, and that happens when you add or subtract outside of the parentheses, outside of the function. Okay, so let's look at a couple of examples where we have a combination and see how we would work with that. Just so we remember. Okay, so combinations of transformations. I've got my little cheat sheet here so we can remember what to do first and second and so on. All right, let's go ahead and look at an example where we're actually given the equation of the function. So, and it'll be something that has a parent function from our library of functions. So for example, what if I asked you to graph f of x equals 2 times x plus 1 squared? Okay, so the first thing you would have to do, since I'm not just giving you the graph, but I'm giving you the equation and expect you to know the parent function, the first thing you would need to do is to identify which parent function from our library of functions. So the key here is the square, right? So if I look at my list of functions from my library of functions, we know that it must be a variation on this function, x squared. And remember that we have 3 key points that we're always going to use for x squared. We're going to have 0, 0, 1, 1, and negative 1, 1. And we're going to want to see what happens to these 3 key points. Okay, so now that I know that I'm going to use the parent function x squared and that I'm going to be interested to see what happens to 0, 0, 1, 1, and negative 1, 1. Oops. Okay, now I'm going to identify what types of transformations I have. I have 2 differences between this function and just x squared, right? First of all, I'm adding 1 inside of the parentheses, and also I'm multiplying by 2 on the outside of the parentheses. So you have to know what kind of a transformation what kind of an effect that's going to have. We know that anything that happens on the inner part of the function is going to affect the x coordinate, and it's going to do so in the opposite of the way that you would expect. So in this case, since it's plus 1, you're actually going to subtract 1 from each x coordinate. That's supposed to be minus 1 from each x. Okay, and then whenever something happens on the outside of the function, that affects the y coordinates. And in this case, it's going to multiply 2 times each y, which is going to have the effect of stretching it. So this one over here, the subtracting 1 is going to affect, it's going to give us a horizontal shift. And doubling each y coordinate, what kind of effect is that going to have? So that's going to stretch the function vertically, right? Vertical stretch. All right, so let's come back over here and see what we've got is a horizontal shift and a vertical stretch. So that is number 1 and number 2. So we're gonna shift horizontally first, and then we're going to do our stretch or shrinking. All right, so let's start by performing our horizontal shift, which is subtracting 1 from each x. So when we shift x squared horizontally, we end up at -1, 0, and we end up at subtracting 1 from 1, we're going to get 0, 1, and subtracting 1 from -1 is going to give us -2, 1. All right, let's go ahead and plot that to see where we are. This is just the first step, horizontal shift, affecting the x coordinate. Okay, so we are at, so far, -1, 0, 0, 1, and -2, 1. Let me zoom in a little bit more. Okay, so -1, 0, 0, 1, -2, 1. You see how that looks like the parabola that we're familiar with, but it's shifted to the left 1 unit. Okay, so that would just be the part of our function. This would actually be the graph of f of x equals x plus 1 squared. Or maybe I won't call it f of x because I don't want to confuse it with the other function, but let's just call it y. This would be the graph of y equals x plus 1 squared without the 2, okay, because we took care of the horizontal shift. But now we're going to take care of the stretch. Stretching by a factor of 2, which just means that we're multiplying each y coordinate by 2. So I'm doing this in a separate step so that I make sure that I do it in the right order. And what I'm going to do is multiply each y coordinate by 2. So for example, the point -1, 0 is going to end up being what? Still -1, 0. The point 0, 1 is going to be 0, 2 when I double the y coordinate. Zero, 2. And the point -2, 1 is going to be -2, 2. So let's go ahead and plot those points. -1, 0 stays the same, it doesn't stretch. But 0, 1 is going to become 0, 2. Doubling the y coordinate. It hates it when I drop dots on here. Sorry. Let's make it an x instead. 0, 2. And then -2, 2. And so we get this graph here. Oop, it's a little crooked, sorry. It's supposed to be a nice smooth round curve, let's all pretend. All right. Okay, so you notice that it looks kind of skinnier But really what the way we're thinking of it is as a vertical stretch. So it's getting further away from the x-axis. So this graph in blue, that's our f of x. Make sure that when you're graphing on the test, if you don't have, two different colors, you might want to make one of them dotted and one of them solid, something to indicate what is the final graph labeled as f. Okay? So that's what I mean by performing it in this particular order. Because in some cases, depending on the combination of transformations, if you perform it in the wrong order, you'll end up with the wrong graph. But I want to reassure you that you can always check. Because if you got it right, these final points, which the final points on the graph we had were -1, 0, 0, 2, and -2, 2, those final points should satisfy the equation f of x equals 2 times x plus squared. So let's just check. For example, if I plug in -1 to f, I should get 0. Let's see, -1 plus 1 squared. So we get 2 times 0 squared equals 0. So yeah, it should go through the point -1, 0. I can 3 of the points if I want to. So 0, 2 is another one. If I plug in 0, I should get 2. Let's see. F of 0 equals 2 times 0 plus 1 squared. It's 2 times 1, which is 2. So that worked as well. And lastly, I should get -2, 2 should also be a point on the graph. So let's see, we have f of -2, 2 times -2 plus 1 squared. It's going to be 2 times 1, which is 2. Okay, so that one worked as well. So in the end, after you do several transformations, if you're not quite confident, you can still just plug in those values. So why do we need to specifically move these key points? Well, because those are where important changes happen in the function. So if we just randomly graphed points, we might get a part of the function that's off to the side here that maybe looks like a line. We don't actually get the important part, which is the part where it turns around. We need to be able to see the shape of the function. Okay, let's see. I'm gonna check if we have any questions. No questions so far. Okay. All right, let me try to do one more before we finish here. I'm going to copy down my cheat sheet. Keep that with you until you memorize it. Okay, so what if I asked you to graph, let's do f of x equals, we'll do the negative or opposite of the square root of, and we'll do x plus 2 plus 1. Okay, so the plus 2 is inside the square root and the plus 1 is on the outside. The negative is on the outside as well. So we have 3 different transformations of what parent function. So let's go back to our library of functions. So from our library of functions, we have to decide which function we're shifting around, right? And our function that we're graphing has a square root in it. So it must be that we're shifting around the square root function. So Our square root function, look, has a key point at 0, 0. Remember I said use x values that are easy to take the square root of. 0, square root is 0. 1, the square root is 1. And the other one that's easy is 4. So the square root of 4 is 2. So we're going to use the key points 0, 0, 1, 1, and 4, 2, and we're going to move those around. We're going to have 3 transformations this time. Okay, so we're going to use the parent function y equals the square root of x. And the difference now between our new function, we're having some problems here. Sorry guys, the stream is cutting out. Hopefully that'll be the last time. Okay, so our new function has 3 variations here. We have the negation out front, we have adding 2 under the square root, and we have adding 1 outside of the square root. All right, so the only one that's going to affect the x coordinate is this one. That's the inner part of the function. And remember, when you add or subtract to the x, you're going to add or subtract the opposite actually of what you see here to the x coordinate. So in this case, we're going to subtract 2 from each x coordinate. And what effect does that have when you subtract 2 from each x coordinate? We're going to shift horizontally to the left. Okay, so that's one of the changes. Another change, which is on the outer part of the function, so it affects the y coordinate, is we're going to add 1 to each y coordinate. So we're going to add 1 to y. And when we do that, it has the effect of shifting vertically, right, upward 1 unit. And then over here, the negation, again, is on the outer part of the function. And so it's going to negate the y coordinate. It affects the y coordinate by negating it. So we're going to take the opposite of y. Replace each y with negative y, in other words. Okay, so what happens when you replace y with negative y? You're going to reflect vertically, right? Reflection. Oof, it's getting hard to write there. Let me zoom in. So we have a vertical reflection when we change the sign of every y. Okay, so out of our list, we have a horizontal shift. Okay, that's where we subtract 2 from each x. We have a vertical shift. That's not down until the 4th step. This is where we're going to add 1 to each y. And then we have a reflection. It happens to be a vertical reflection, which we're replacing each y with its opposite. Okay, so we have to do this in this order to guarantee that we get the right graph in the end. All right, so let's start drawing. Let's see, first actually, I'm going to start with my key points from square root. Remember we had 0, 0, we had 1, 1, and we had 4, 2. And we already know the original graph, what it looks like. Looks like this. Starts at 0, 0, 1, 1, 4, 2. Looks like a half of a parabola going off into the right. Okay, so now what we're going to do is we're going to subtract 2 from each x, or in other words, shift to the left horizontally. So the new points that I'm going to label on this first phase of my transformation is going to be -2, 0, -1, 1, and 2, 2, subtracting 2 from each x coordinate. All right, so the first phase of my transformation, oops. The first phase of my transformation, we're going to plot -2, 0, -1, 1, and 2, 2. So you see it looks just like my original graph, but shifted 2 units to the left. I'm going to label these right on the graph, and that's how I want you to do it on the test, okay? All right, so we did our horizontal shift to the left. The next thing we need to do is the reflection. There, we would have done stretching or shrinking if there was any, but there's not. So now we're going to do the reflecting. So remember what kind of reflection we had here? It was a vertical reflection because the negative's outside of the function, outside of the square root. We're replacing every y with its opposite. Now, -2, 0, that guy, the opposite of 0 is still 0. So for that one, we're just going to have -2, 0 again. That one's not going to move. But -1, 1 is instead going to become -1, -1. And 2, 2 is going to become 2, -2, replacing each y with its opposite. So we still have -2, 0 there, but we're moving to -1, -1, and 2, -2. Okay, so that has the effect of reflecting that function over the y-axis, and it looks like this now. Okay. By the way, the equation of this one would have been the same as the square root of x, but just adding 1 inside. And what we've just gotten here is we've done the second transformation, which was the reflection. So that would be the same as this guy here. All right, but we still need to do the last phase, which is what I highlighted in blue up there, the adding the 1. The adding the 1 to every y is a vertical shift. That's the fourth step in our order of transformations there. And we have to add 1 to every y coordinate. Because it's outside the function, it affects the y. All right, so let's go to black now. So if we add 1 to each y, let's see what we get. We're going to get -2, 1. For this point, it's going to go to -1, 0. And this point is going to go to 2, -1. Shifting each point up 1. You can just do that on the graph if you want to, but I find a lot of people like to do the arithmetic way, so I like to do it that way too. So shifting up 1 from -2, 0, we're going to be at -2, 1. Shifting up 1 from -1, +1 puts us at -1, 0. Oh, don't do that to me. There we go. -1, 0 is about there. Maybe zoom in a little bit. Okay, -1, 0, and then -2, -2 moves up to -2, -1. Okay, so this is the same as this green graph, but shifted up 1 unit. So it still has the same shape, just shifted up. All right, so this is our actual function, f of x equals -square-root of x. Ooh, I put +1 under there, and that should have been a +2. Sorry about that. Hope that didn't confuse you too much. So that should have been a +2. Remember, we moved 2 units to the left. And then now we've added the 1 to it. So we've done all 3 of the transformations. So the graph in black there is our final graph. Now, suppose you're a little unsure, maybe I didn't get my order right, you're working it on the test and you're not sure if you got the order right. Remember, you can always plug in these last points and see if they satisfy the function. So these points here should satisfy this function. So if you plug in each of the x coordinates, you should get the right y coordinate out. So let's see. What if, I'm going to erase this original function here. Okay, so we have f of, for example, -2. If I plug that in, we're going to have -2 plus 2 plus 1. So that's going to be 0 plus 1 is 1. And you can see we did have 1 was our y value, so that's good. All right, and let's plug in the next x, which was -1. So that would give us negative of -1 plus 2 plus 1. So that's going to be the opposite of square root of 1 plus 1. This is going to give us 0, which is what we had here. Okay, and then lastly, 2 -1 is supposed to be on there. So plugging in 2, we should get -1. Do we? Let's see. Negative square root 2 plus 2 plus 1. It's going to be the opposite of the square root of 4. So -2 plus 1, which gives us -1, just like we were supposed to have. Okay, so it looks like that we did our order of our transformations correctly, and that actually is the shape of the function. So I hope you guys found this helpful. I don't want you to worry that every single graph on the test is going to be like this one. No. This would be, the hardest possible function that I would expect you to graph. So it's not like every single one's going to be like this. This is kind of the culmination of all the transformations. So, but what is important is that you learn your library of functions and that you learn what effect each type of transformation has on a graph. So for the most part, you're going to just have like one transformation. I'll have questions where you have to identify which function is which, and I'll have questions where you're given maybe f of x equals absolute value of x minus 2, something like that. Some of them you will just identify the graph from a multiple choice, but there will be one or two where you're going to have to actually graph it on paper. So do be prepared for that. You'll be allowed to bring in graphing paper, by the way. So that's all for tonight. And if you have any questions, you can feel free to email me. Thank you for attending, and you'll get your bonus points. And those folks who are watching the video at home, you need to post, a recorded version, not the live version. They're going to need to post a quote as well from the video. So include your name, the days and times, and know that it's not going to be like that, Melvin. Not every single graph is going to be like that. So, yeah, when you watch the recorded version, you need to post a quote. Okay, have a good night. Have a good weekend. And I am pushing the date of the test, the due date, back to Thursday. So be looking for your announcements in D2L. Good night, everybody.